Welcome back. So we're back to a group theory. We talked a lot about steerable neural networks already, about the Clebsch-Gordan tensor product is mentioned a lot of times already. And I think in order to properly understand literature and be able to work with it, we also need to learn a bit more about the actual representation theory of the SO3, the 3D rotation group. So we're going to learn about the irreducible representations of SO3, which are called the Wigner-D matrices, and the Clebsch-Gordan tensor product, which is a tensor product that maps between steerable vector spaces. And I think after this video, we're ready to dive into the literature again, and we are all set to start building our own three-dimensional group convolutional neural networks or group equivariant graph neural networks. Okay, recall from lecture 2.3 that when we talk about irreducible representations, two things are important. Firstly, we have this equivalence of a representation. That is, if I have some representation which transforms a vector, I can write it to an equivalent representation via a change of basis. And so that's the first thing. And the second thing, through such a change of basis, I could also find a block diagonal form, which is like a very convenient form of a representation, because each representation in these blocks only transforms part of the vector on which it acts, right? This block only acts on these rows in the vector, and this vector, matrix block transforms only another subspace of my vector on which this entire representation acts. So oftentimes it's convenient to write representations in terms of irreducible representations because it allows us to restrict the computations only to these small subspaces. Okay, and we learned that if we have such a vector with a representation acting on it, for example, the regular representation, then we can find an equivalent representation that has this block diagonal form via change of basis, which corresponds to a Fourier transformation. And these sub-representations along the diagonal are called irreducible representations. So now when we talk about the group of 3D rotations, SO3, and their irreducible representations, we talk about Wigner-D matrices. So similar to the circular harmonics case, so which are irreps of SO2, these irreps are indexed with a frequency index. So we have these waveforms with a particular frequency. Also, such a notion exists for the SO3 case. However, now these representations are not scalar valued, but they're matrix valued, so they're matrices. And the dimension of these matrices corresponds to 2l plus 1 by 2l plus 1, where L is this sort of frequency index. Okay, so the irreducible representations of SO3 are these 2l plus 1 square dimensional rotation matrices, which can no longer be further reduced to matrices of a smaller size. And these matrices in terms, so they're 2l plus 1 by 2l plus 1, consist of these functions. So the matrix elements are sometimes referred to as the Wigner-D functions. And just like the irreps of SO2 form an orthogonal basis for SO2 or for the one ring S1, so do these Wigner-D functions form an orthogonal basis for functions on SO3. And I'll say a bit more about it in subsequent slides. Now, a bit of terminology. These 2l plus 1 by 2l plus 1 dimensional matrices, of course, act on 2l plus 1 dimensional vector spaces. And we call such a vector space a steerable vector space of type L. So we denote this vector space with V subscript L, which is actually equivalent to just the Euclidean vector space 2l plus 1 of dimension 2l plus 1. But with this, we can make explicit what is the dimension of the space and have a more compact notation. Similarly, a vector in such a steerable vector space will be called a type L vector. Okay, so let's have a look at some examples of Wigner-D matrices. This is a somewhat trivial example that of a type 0 steerable vector, which is really just a scalar because 2 times 0 plus 1 is a one-dimensional vector, so a scalar. And we know that scalars cannot contain any form of directional information in them. And so they trivially transform via the representation of the rotation group. I cannot rotate a scalar. I just multiply it with the value 1. So the 1 by 1 dimensional irreducible representation of the rotation group is just the constant 1. And before we've been representing scalar values with just dots, no directional information in it. And if I rotate it, it stays the same dot. Okay, so the type 0 vectors are scalars and they trivially transform. Then we have type 1 vectors, and those are 2l plus 1. So that's 2 plus 1 is 3-dimensional vectors, and those are the 3-dimensional vectors that we're kind of familiar with, right? Like velocity vectors or forces or displacement vectors. And these transform directly via the rotation matrices themselves. So the type 1 Wigner-D matrices, are really just the rotation matrices themselves. And they may look something like this in a particular alpha, beta, gamma parameterization, where these correspond to some Euler angles, right? Okay, so these Wigner-D matrices are really 2l plus 1 by 2l plus 1 dimensional matrices. For type 1, it's a 3 by 3 matrix, and their elements consist of these functions that depend on the group, here explicit in alpha, beta, gamma coordinates, and these functions are called the Wigner-D functions. And each of these matrix elements, each of these functions is orthogonal to one another. So this function is orthogonal to all these other functions in this matrix. And so it happens to be that all these functions in these irreducible representations are indeed orthogonal to each other, and they form a complete orthogonal basis for SO3, which really means that we can think of them as a Fourier basis for functions on SO3. So any function can thus be represented as a Fourier series or as a weighted sum of these Wigner-D functions weighted with some Fourier coefficient. All right, we had all these different irreducible representations indexed with their type or frequency index L, and they were 2l plus 1 dimensional matrices. So we run M index from minus L to plus L and also from minus L to plus L. So this sum, these three sums sum over all possible Wigner-D functions, over all possible orthogonal functions on SO3. And this summation over here can actually be conveniently written in this trace form, because now we only sum over the frequency index, which is a kind of idea that we're familiar with Fourier series, that we take a series over all these frequencies of the trace of the matrix product of these two matrix valued coefficients and these matrix valued representations. And I write it in such a form because previously I mentioned that we have such a thing as a generalized Fourier transform on compact groups, where we had in the forward Fourier transform, we just compute the integral of a function with our representations. And if our representations are matrix valued, such as now we have Wigner-D matrices as irreducible representations, then also these coefficients are matrix valued. And then we also need an inverse Fourier transform coming from this matrix valued Fourier coefficient and these matrix valued representations. And this summing, so here we have a sum over M and over N, that is actually done in this matrix multiplication, right? Because I do sum over all the rows and the columns then in this matrix. So that takes care of one of these sums, and then the trace takes care of the other sum. So this trace is a way of sort of getting rid of these double sums notation. Okay, so now I actually don't care that much how you precisely write it down. The important thing is here that we have also now for functions on SO3 a Fourier transform. And this Fourier transform is obtained in terms of these Wigner-D functions or in terms of these irreducible representations. Now, there's an interesting aspect about these Wigner-D matrices, and that is that their central columns are actually invariant to rotations around a particular reference axis. And what does it mean? I recall from one of the previous lectures, lecture 1.6, that we can think of the two-sphere as a homogeneous space of SO3. So imagine these three rotation angles, alpha, beta, gamma, where maybe alpha is maybe depicted in this radial axis. Then suppose I have a symmetric object, then rotation around this alpha axis doesn't change this object. So it all these rotations are identified with one and the same point on the sphere. And this allowed us to consider the sphere S2 as a homogeneous space of SO3, or as a quotient space. And now what does this statement tell us? That the central columns are invariant to such rotations. It means actually that the central columns can be thought of as functions on the sphere. And maybe if we go back to the previous slide, here we had one of such irreducible representations where we had alpha, beta, gamma axis. We see actually that this column doesn't depend on alpha, so I can rotate whatever I want around this axis. It doesn't change anything. And so what's left, these functions only depend on these betas and gammas. So this column actually represents functions on the sphere, because functions on the sphere, or the sphere, any point on the sphere can be reached with only just 2 rotations, these Euler angles. Yeah, so these central columns are really just functions on the sphere, and they so happen to be coinciding with the spherical harmonics. And maybe to some this isn't that coincidental. If you really dive deeply into the theory, this at some point becomes completely obvious, but that's way beyond the scope of these lectures. The nice thing is that now that here we have a complete orthogonal basis, these Wigner-D functions form a complete orthogonal basis on SO3, and the spherical harmonics, which are a subset of these functions, actually form a complete orthogonal basis for functions on the sphere. And these functions on the sphere, these spherical harmonics, they look something like this. So this is what the central columns look like in a glyph visualization. Where the glyph visualization means that if I have a large value in a particular direction, then I scale this blob in that direction. If I small value, then I shrink it. And I do that with the absolute value of the function in that particular direction. For every direction, I can sample the value. For example, in this direction, it's a high value in that direction, so it's elongated. Perpendicular to this direction, I have a 0 of this spherical harmonic, so that really shrinks it to this point. And then in the opposite direction, I have a high value again, or actually a highly negative value. So these blobs are color-coded with blue meaning negative value, yellow meaning positive values, or actually the other way around, I think. And from these glyph visualizations, we also see that in whatever direction I look for the type 0 representation, which we know is invariant to all these rotations, and whatever direction I look, the value of the spherical harmonic stays the same. So this is really just a constant. And then actually from top to bottom, we have the L index, right? So this is L is 0, this is the type 1 spherical harmonics, and then the next one type 2 and type 3 spherical harmonics. And these are really the central columns, now visualized as rows, but the central columns of these Wigner-D matrices. Yeah, okay, so the spherical harmonics coincide with these central columns of these Wigner-D matrices. They are called harmonics because they are solutions to a Laplace equation, and solutions to Laplace equations are called harmonic functions. They form a Fourier basis on the sphere S2 in a similar way that the circular harmonics form a Fourier basis on the ring, on S1, and the Wigner-D functions form a Fourier basis on SO3. That also means that we can project functions onto this basis, and then in this basis, these type of vectors, they transform via the Wigner-D matrices. So if I stack all these Fourier vectors on top of each other, I have one big vector which transforms in a block diagonal way, where each of these matrices is one Wigner-D matrix of type L. So this is again the Fourier shift theorem at work. If I want to rotate a function on the sphere, I can first do Fourier transform, shift it via the Wigner-D matrices, and then, or the irreducible representations, and then do the inverse Fourier transform. Now the fact that these spherical harmonics transform via the Wigner-D matrices, that actually directly follows from the fact that these spherical harmonics coincide with the central columns of these Wigner-D matrices. The Wigner-D matrices are representations, right? So a rotation of the input can also be obtained by just splitting this matrix in these two representations, right? And since all these columns transform independently from one another with one and the same rotation matrix, we directly obtain that the rotation of these spherical harmonics is simply obtained by multiplying this spherical harmonic vector with the corresponding Wigner-D matrix. Okay, so this is nice. So it tells us that the spherical harmonics embeddings of directions give us a steerable vector. So the spherical harmonics form a steerable basis. So that also means that if we want to use directional information in our neural network, then we can always embed such a direction vector into spherical harmonics by simply evaluating it, evaluating the spherical harmonic basis function, and that gives us a steerable vector, which correspond to these kind of steerable basis functions. And what's actually happening here is that these A hats can be thought of as a Fourier transform of a Dirac delta, right? Pointing in this direction. If I integrate the spherical harmonics with these Dirac deltas, that means I'm just sampling at those locations. And then I can visualize it also as a function. So if I treat indeed these spherical harmonics embeddings as the Fourier coefficients, then I can plot it as a function where I do this inverse Fourier transform. So the Fourier basis function or the spherical harmonics multiplied with its coefficient and sum them all together. And that gives us this glyph plot. So a function that has high values in this direction, 0 orthogonal to it, and maybe some oscillations in the perpendicular, or like in the anti-parallel direction. Okay, so there's two things going on. Direction vectors can be equivariantly embedded into the steerable vector space via the spherical harmonics evaluation, meaning that if my vector rotates, so if I rotate my vector, then the spherical harmonic embedding of this rotated vector corresponds actually to my original embedded vector, and then rotated afterwards via the Wigner-D matrices. So when thinking of the spherical harmonics as embedding functions, we see that these embedding functions are indeed equivariant. And secondly, and maybe this is not so important in practice, but maybe conceptually it's interesting to think about it, that here we really have a geometric quantity, a vector, and we convert it into a functional form. So we can really think of it as a function which has a function on the sphere whose value changes with every direction. Okay, so now we talked about irreducible representations of SO3 and steerable vector spaces, and we also talked about a steerable basis on the sphere, namely the spherical harmonics and steerable embedding functions to compute attributes from geometric quantities that are steerable. Now what remains is to introduce a computational tools to start transforming these steerable attribute vectors, and we'll do that via the tensor product, the Clebsch-Gordan tensor product. And the idea here is as follows. Now, suppose I take the tensor product of two steerable vectors, where the tensor product is really this, in the general sense, multiplying all of the elements with one another, right? So I take the outer product with A and B, and from this general tensor product, I can derive several other tensor products, right? I can derive the inner product. The inner product is the trace. I could derive a cross product from this tensor product, which the cross product, remember, also takes two vectors as input and spits out a new vector by taking a particular combination of elements in this tensor product. And of course, the full tensor product or outer product is given over here. Now, the idea is that if my two vectors are indeed steerable vectors, then the resulting tensor product is again a steerable vector. And that is visualized as follows, right? Suppose I know my input vectors transform via their respective representation. So I have a representation acting on vector A and one on B. So I color-coded this with red and green. So the red one acts on the left, the green one on the right. Right? That's just filling in this replacement over here. So this tensor product is squeezed in between these two representations. Now, when we talked about steerable vector spaces, we talked about vector spaces and not matrices. But we can vectorize this matrix, right? By just flattening it and stacking all these columns on top of each other. So we have this vectorization procedure. And there is this identity which quite often pops up if you study these papers on Clebsch-Gordan tensor product. It's a convenient property. If I vectorize the product of matrices, I could also write this as a vectorization of this matrix X and then multiply it with one big matrix, which is the chronicle product between B transpose and A. So if we apply this identity to the above, so we have this tensor product and we vectorize this tensor product, then this vectorized tensor product transforms also via a matrix, via this matrix, which is given as a canonical product between this representation and this representation. So it really will be again one big matrix that in some way depends on R. And it is a representation. So maybe let's just write this is one big matrix that depends on R, and it is a representation. Okay, so what does it tell us? It tells us that if I take a tensor product between two steerable vectors and I flatten this via this vectorization, then this again gives us a steerable vector which transforms via this representation. And we know from this equivalence of representations that we can again block diagonalize this representation to its form, which only includes irreducible representations. And that looks like this. So apparently this tensor product, I can flatten it. I can do a change of basis such that the elements in these vectors transform independently from one another. So we create these independent subspaces where each subspace transforms with its own irreducible representation. And it could be that we have some representations occurring more than once, for example, a type 1 representation, then a type 2 representation. That can happen. And then we say that such an irreducible representation occurs, enters in this big matrix with a certain multiplicity. But the idea here is that this tensor product is an equivariant mapping, meaning that we also have a representation on the output of this operation, and we can write this representation in block diagonal form, in this convenient form. And now that is precisely what the Clebsch-Gordan tensor product does for us. So this change of basis, these Q's that you just saw, are merged inside the definition of this Clebsch-Gordan tensor product. Because I can, when computing this Clebsch-Gordan tensor product, all this multiplication, also at the same time encode for this change of basis, which is really like a linear transformation in itself. So I might as well incorporate that in our bilinear Clebsch-Gordan tensor product. Okay, so the Clebsch-Gordan tensor product incorporates this change of basis such that the output of this vector is directly placed in a basis which is transformed in this block diagonal form via irreducible representations. Okay, so the idea is that this vectorized tensor product gives us a part of this vector which transformed with frequency L1. Then there's a part of this vector which transformed with frequency L2, etc. So we create this all vector which is split into these individual subspaces. So let's take a look at what it's going to look like. So again, suppose we have two input steerable vectors of type L1 and L2 respectively. So this one transforms via Wigner-D matrices of type L1 and this one with L2. Now the Clebsch-Gordan tensor product is defined by these Clebsch-Gordan coefficients that tells me which multiplications can I perform as to obtain an output vector which transforms under type L. So via a Wigner-D matrix of type L. So if I want to make a type L steerable vector out of these two steerable vectors transforming under L1 and L2, I need to make a linear combinations of their components in a particular way. These products of these two vectors, but not all products are allowed. And maybe that's most intuitively explained with an example. For example, if I have the product of two scalars, so that's about two type 0 representation vectors, or type 0 vectors, just scalars. It's like type 0 times type 0 is an output, L is 0. So actually this C is just a 1. If I want to type 0, L is 0 output, with a 0 input, then this Clebsch-Gordan tensor product is 1. 1 times that scalar, and that scalar gives me the output scalar. I can also think of a scalar vector product, where the first element is a type 0 vector, so a scalar. The second one is really a vector consisting of these 1, 2, 3 elements. So this is just a scalar, and the other one is a vector. This one is indexed with M1, is 0. This one is indexed with M1. Oh, sorry, M2 is -1, 0, 1. And the output is of type 1 with which is a 3-dimensional vector indexed with M is -1, 0, 1. And so in order to obtain the M is -1 component of this type 1 steerable vector, I need to know which multiplications can I perform. So M1 is 0 multiplied with M2 is -1. That's actually ending up over here. This is the scalar product. So the scalar times this element, scalar times that element, and that comes in these places. So that actually tells us that for L is 1 and then M is -1, we have that for the corresponding indices that this Clebsch-Gordan tensor product, it just gives us the value 1. But for all other multiplication, this evaluates to 0, simply because we don't have any more indices to sum over. And now the same for the dot product. In general, this tensor product, there's a lot of possibilities, right? Let's go back to the previous slide. So if I take the tensor product of two three-dimensional vectors, I get this 3x3 matrix. But for the dot product, I'm only interested in this diagonal. So that means a lot of these multiplications should be set to 0, otherwise I do not obtain a scalar value as output. And then so also the cross product is a particular instance of a Clebsch-Gordan tensor product that maps from a type 1 vector, so a 3-dimensional vector times a 3-dimensional vector, and it spits out another type 1 3-dimensional vectors by taking a particular combination of these multiplications. Okay, so this Clebsch-Gordan tensor product encode for all possible multiplications or tensor products between vectors of different types. And in general, many of these possible combinations of multiplications will be 0. And in particular, whenever the output frequency index is below some lower bound and above some other bound. So if I take the tensor product of a type 1 with a type 1 steerable vector, 1 plus 1 is 2, I can create an output steerable vector of type 2. But I cannot go beyond type 2. So anything above this 2 will be non-existent. So in a sense, I can only alternate between adjacent frequencies. Okay, and these tensor products are nicely coded up in this library called Euclidean neural networks, or E3NN. So yes, I think it's many of the papers currently written are based on this very nice and convenient to use library. So let's have a quick look at what we can recognize in this library. Okay, so this is the main GitHub page. So you see all these nice spherical harmonics rotating. There's this nice getting started. And the site, of course, definitely do this. It's a brilliant library. Yeah, let's have a look at the documentation. Okay, yeah, so it's really nicely documented. It already talks about irreducible representations, convolutions, and building your own transformer or convolutional neural network with this. The API talks about representations of O3, some neural network layers, a demonstration for how to get started. So, and this is also working in a similar way as the ESCNN or E2CNN library, where you need to specify the input and output representation type, and then the code takes care of the manipulations. So it explains that if I have a vector of a certain type and another vector of a certain type, I can take their outer product, and this then also transforms via the tensor product of these representations in the following way, right? We just saw that we could vectorize this, and we can write this then also in block diagonal format. That looks something like this. So this library takes care of all the possible allowable tensor product operations for you. So if I take, for example, the full tensor product of irrep, a vector that transforms via the irrep of certain types with another steerable vector, and this is the type specification. So actually in this code, they also work with parity to handle reflections. So we have input vector X is of a certain type, input vector Y is of a certain type. And then with all these multiplications, I can generate several possibilities. I can take inner products that would generate type 0 vectors. I can take cross products between these type 1s and type 1s, and that would give me type 1 steerable vectors. I can also do outer products of type 1 vectors with type 1 vectors, and that gives me type 2 vectors. And so there's all these possible combinations. They identified that as 8 possible trajectories of a type 0 with a type 0 gives a type 0, a type 1 with type 0 gives a type 1, etc. And we can also decide to parameterize this tensor product with weights, and it is going to be important in the neural network setting, but here it's not parameterized. Yeah, and so the nice thing is that they have the layers that do these tensor products for you. So if I take the tensor product, and they also memorize or code this up in such a way that I can always recover the transformation matrix, so the representation that acts on the output of this tensor product. And you see that via this Clebsch-Gordan tensor product, the output will be directly put into this basis, which transforms via these block diagonal representations, where along in each blocks we have the irreducible representations of the corresponding type. So you have 2 features that trivially transform, so these multiplications. We have 4 representations that transform via these type 1 Wigner-D matrices, and we have 2 steerable vector subspaces that transform via type 2 Wigner-D matrices. Okay, so I'll stop here. Maybe I'm not the best person to give a full demo of this library, but there are really nice examples here, a bit more on irreducible representations. There's a nice tutorial on convolution layers made with this E3NN library. And I think many of the SE3 and E3 equivariant graph neural networks make use of this convenient library. So please check it out. It's a really nice one. Okay, so going back to the slide deck. Yeah, so we covered actually all the theory that you need to know to understand and start building your E3 equivariant graph neural networks, especially if you make yourself acquainted with this particular library. Because we've already seen, like in the 2D case, that we came across this Clebsch-Gordan tensor product. Now we actually know what it does. We also saw that in these harmonic networks, we were able to transition between frequencies. We had feature maps that transformed via irreducible representation of a certain frequency. And we can only alternate that much. If I want to go from a frequency, let's say 2 to 0, I need to convolve it with a frequency -2 filter. And that was this equivariance condition. And these conditions are nicely coded up in the Clebsch-Gordan tensor product. And now with this Clebsch-Gordan tensor products in place, we are also able to code up steerable graph neural networks, really as a type of steerable group convolutional neural networks, where we saw, as before, we have a steerable feature vector, and a steerable attribute embedding, for example, through spherical harmonics, or as we have seen before, via circular harmonics. And if we use the notation that this, once evaluated already for the spherical harmonic embedding or the attribute embedding, what remains is just a matrix. So partially evaluated Clebsch-Gordan tensor products are really matrix vector multiplications. And with that, we can also code up what we would call steerable multilayer perceptrons to come up with a nonlinear counterpart of these steerable group convolutional neural networks. Okay, so now when you start reading papers on this topic and you come across such a tensor product, you should realize that this can be thought of as a conditional linear layer. And if it's also defined to be a Clebsch-Gordan tensor product, then it means it's a conditional linear layer that conveniently places the output in a steerable basis, such that these vectors transform in a block diagonal way. Yeah, so I think now we've covered all the theory that we need, and what remains in the subsequent video is a quick analysis or overview of what kind of methods are currently being used with graph neural networks.